Within this video, we're going to look at how we solve radical equations and how we use inverse operations to solve, and looking at a lot of application-based, different formulas that represent different situations and how to solve those, but also checking your work to see is the answer reasonable. So the first example is a formula that represents braking speed. And so if speed equals 22 times d, 22 being I believe a friction coefficient that's part of this formula. So we're saying if we know distance, which is 130 feet, that's how far the skid mark would be. And we're going to take 22 and multiply it by 130. That would give us a radicand of 2,860. And so in your calculator, to compute that, you're just going to go to second x squared. Notice it pulls up the radical symbol. And you're going to type in 2,860. And this is going to give an approximation of how fast. So it's about 53 miles per hour. So what was the speed of a car or vehicle, a car that's had roughly 130 foot skid mark? And we're measuring, trying to find that speed in miles per hour. Would be 53 miles per hour. Second, we've got the same formula, different situation, because it says if the car is traveling at 40 miles an hour, how far will it travel? So now we know that it's 40 miles an hour, and we've got 22 times the distance. So here's what we have. We're trying to solve for d, which is inside the radical. It's part of the radicand. Now remember, this can also be written as an understood root of 2. So this would be 22d to the 1/2 power. And one of our exponent rules when we raise a power rule is if I raise this to the second power, then I got to raise this to the second power. So 40 squared gives me 1,600. And notice what happens when I take a power to a power. 1/2 of 2 is just 1, so I get 22d. And then I want to take 1,600 and I want to divide it by 22d, and I'm going to get approximately d is equal to saying how far will the skid mark be. So it's about approximately 73 feet with 40 miles an hour. Third example, we're thinking about a tsunami. Tidal wave can be modeled by this equation. And it says, well, if the speed is 356 times the square root of d, speed is equal to 356 coefficient times square root of d. Well, part A says, well, what's the speed if the tsunami has a water depth of 512 thousandths of a kilometer? So we're looking for speed in kilometers per hour. So for part A, speed would be 356 times the square root of 512. And that would be the same as 356 times 512 thousandths to the 1/2 power. So if you want to compute that, you could type in 356 times second x squared and then type in 512 thousandths and hit enter. And that just means that it's about 254 kilometers per hour. So back to the context here, it says, what's the speed? Well, the speed would be about 254 kilometers per hour. So part B says, we'll take this equation, speed equals 356 times the square root of d, and solve it for d. Well, we also know, as we showed up here in the line above, that it could be written as d to the 1/2 power. Well, what if a tsunami is found to be traveling at 120 kilometers? So we could go ahead and substitute 120 in for the speed. Well, you want to solve for d, which means 356 is being multiplied by that. So I'm going to divide 120 by 356. And then I have d to the 1/2 power. So if I want to solve for just d, then I need to square both sides. So when I do that, I'm just going to type in 120 divided by 356 in my calculator in a parentheses. So I'm going to open parentheses, 120 divided by 356, and I'm going to close it. I want to square it, and I should get about 11 hundredths. And that just means that the depth, what is the average depth of water? That just means that the final result, d, is equal to 11 hundredths kilometers. 11 hundredths of a kilometer. So next example, we've got a population function that models how a population is growing, and it's increasing slowly. And so the population is measured in millions, and t is the time in years. So how many years will it take for Apple Island to reach 121 million? So this right here, this is p of t. This is a function notation. We're calling the function p, which is representing population, and it's a function of time. So we are trying to solve for what time would be. Well, we know that the population at a certain time is going to be 121 million, and then that's going to be 88 2/10 times 1 plus 13 hundredths t under the radical. Now this is the radical form, and we know what the rational form would look like. It would be 88 2/10 times 1 plus 13 hundredths t to the 1/2 power. Well, in order to start to isolate t, I've got to start peeling numbers away from it. I have to do different operations. So I'm going to divide both sides by 88 2/10, which is what I would do over here in the rational form. And what I would get is about 1/372 thousandths after I divide out. And then I'm left with 1 plus 13 hundredths t, or if I want to use the rational form, 1/372 thousandths equals 1 plus 13 hundredths t to the 1/2 power. Now we know what we're going to do here to solve for t with this being raised to the 1/2 power is we're going to square both sides. Now, I'm showing you in this rational form because we know we can use the power rule to simplify that. And if we square that term, we should get about 1 88/100. Well, with the radical and the understood root of 2, you can just go ahead and square both sides. And we know what will happen to the radical symbol. It will disappear, just like when we take a power to a power, that exponent becomes 1. So when we square a radical, when we square a square root, we would get what's under the radical sign. And so I'm going to subtract 1 from both sides, just like I would subtract 1 from both sides here. And I'm going to get 88/100 is equal to 13/100 times t, and 88/100 is equal to 13/100 times t. And when you divide 88/100 by 13/100, should get about 6 7/10, so a little bit more than 6.5 years. Because that's what you were solving for in this problem, was how many years will it take for Apple Island to reach 121 million? So this 88 2/10 is approximately that initial population at the time, and it would take about 6 7/100 years to reach that population. So as we noticed in the last few problems when we worked, anytime we saw a radical, we could square it because it was an understood root of 2. We could square both sides to eliminate the radical to then begin working with inside the radicand. So in a thunderstorm, we've got another function, V representing the velocity and P representing air pressure in millibars. And it's just a unit of measurement in meteorology. And so P is the air pressure in millibars. So what is the air pressure of a thunderstorm which the wind has a velocity of 49 3/10? So 49 3/10 will take the place of V of P. And then I've got 5 7/10 times 998 minus P. So since this is understood root of 2, there is no root written there, so it's understood. So I'm just going to square both sides. And when you square, well, let me back up. I got ahead of myself. Before I square both sides, I do have this constant of 5 7/10. I'm going to go ahead and divide by 5 7/10 on both sides. So 49 3/10 divided by 5 7/10 should be about 8 649 thousandths is equal to the square root of 998 minus P. Now I can square both sides. And when I square 8 649 thousandths, I should get approximately 74 8/10. And then that frees up the radicand, which would be 998 minus P. So what I'm going to do is just add P and subtract 74 8/10. So I just move the P variable to the left side and move the 74 8/10 to the other side. So P's on the left now is positive. So P ought to be 900, excuse me, 923 2/10 millibars as part of this formula. P representing air pressure in millibars for this function in regard to velocity of a thunderstorm. Example 5 discusses Beaufort wind scale, and it was devised to measure wind speed, and there's a link in the presentation that'll take you to kind of where that was developed and the numbers that are used. Beaufort numbers represent from 0 to 12 and can be modeled by this function. So this S represents speed of the wind. If we said Beaufort, the Beaufort scale was 11. So that's just going to be substituted in for B. So what we're going to have is 11 equals 1 69/100 times S plus 4 45/100 minus 3 49/100. Notice this 3 49/100 is not under the radical. So since it's not, it doesn't have to be squared at any point. Notice that the understood index here, the understood root is 2, so we know that we're going to square both sides at some point. So this is very similar. I'm going to write it and then I'm going to erase it, but this would be very similar if you had something like this. 11, the 1 69/100 is similar to the 2, the radical similar to a variable, and you're subtracting. Well, if you were going to solve this, you would add the 4, you would divide by 2, you would do inverse operations. And that's what we're going to do here. We're going to add the 3 49/100 to both sides. So that's going to give 14 49/100 as part of the left side of the equation. And then I've got 1 69/100 times S plus 4 45/100 under the radical. So again, this 1 69/100 is being multiplied, so I'm going to do the inverse and divide it. And that will divide out. And so now if you divide 14 49/100 by 1 69/100, you're going to get approximately 8 57/100 with maybe I believe some rounding. And just double checking that. There's just some rounding there to 2 decimal points. So 8 57/100 is equal to S plus 4 45/100. And so that's the only expression I have left is under the radical. So I'm going to square both sides. And 8 57/100 squared is approximately 73.5. And when I square the radical, I'm just going to get the radicand, so S plus 4 45/100. I'm then going to subtract 4 45/100 from both sides, and that should give me the speed. And the speed, 73.5, take away 4 45/100 is 69 500. So the speed is approximately 69 miles per hour. And for a Beaufort scale of 11, winds of 69 and up should represent that Beaufort scale of 11. So if you're looking at different Beaufort numbers, 0 to 12, it would be substituted here for B. So if the Beaufort wind scale was 6, then 6 would be substituted in instead of 11, and then the process goes forward. So with these next few, we don't have any context to them. They're just practice examples. And let's take A. We've got negative 12 equals negative 6 times x plus 4. Notice the variable is under the radical. So I'm going to start out by dividing by negative 6. So that's going to give me 2 is equal to the square root of x plus 4. And I need to get inside the radicand there. So I'm going to square both sides. So that would give me 4 is equal to x plus 4. So if I subtract 4, I get x to be 0. Now if I go to substitute here, I get negative 12 is equal to negative 6 times the square root of 0 plus 4, which would just be 4. And the square root of 4 is 2, and negative 6 times 2 equals negative 12. So x equals 0 is the correct solution. There is not an extraneous solution at this point. All right, so let's look at part B. We got the square root of x plus 4 minus 1 is equal to 7. So since this subtract 1 is not under the radical, I'm going to go ahead and add 1. And that would give me 8. X plus, so the square root of x plus 4 is equal to 8. And I want to get into that variable there, so I'm going to square both sides. So squaring both sides, that's going to give me x plus 4 is equal to 8 squared, which is 64. And then when I subtract 4, I'll get x equals 60. So I want to test that. So the square root of 60 plus 4, I'm just substituting back into the original. Take away 1, better equal 7. So 60 plus 4 is the square root of 64. Square root of 64 is 8. 8 minus 1. 7 equals 7. Checks. And this checks. So part C. Notice I have radicals on both sides. So I'm just going to square both sides of the radical, both sides of the equation. So if I square the left side, I'm just going to get 3x plus 12. And if I square the right side, I'm going to get x plus 8. And now from this point, there's no radicals. It's just subtracting x. Get my variables on one side. I'm going to subtract 12. So 3x minus x, I get 2x. Subtract 12 over here, I get negative 4. So divide by 2, I get x equal negative 2. So I just want to check that. So I'm going to substitute negative 2 here and here. So that'll be negative 6 plus 12, square root of that, sum, and negative 2 plus 8, and the square root of that, sum. Well, this will be negative 6 plus 12 would be the square root of 6. Negative 2 plus 8 would be square root of 6. That checks. So x equal negative 2 is correct. And then two more. Part D. Notice where the radical is located. It's inside the radicand. It's inside the radical, so it's part of the radicand. I see the 4 here. I want to subtract 4. So that's going to give me the square root of negative 3x plus 10 is equal to 3. And I want to square both sides. So that's going to give me 9, and that'll give me negative 3x plus 10. And then I want to subtract 10, and that's going to give me negative 3x equal negative 1. So if you keep simplifying, you're going to get x equal 1/3. So we want to check and see if that's going to be the correct solution. So 4 plus square root negative 3 times 1/3 plus 10 is equal to 7. So what's negative 3 times 1/3? Well, that's negative 1 plus 10. Negative 1 plus 10 is 9. Don't forget my addition sign there. So that'll be 4 plus the square root of 9 is equal to 7. And then this will be 4 plus 3. Taking the principal square root here, and I get 7 equals 7. That checks, which means that x equal 1/3 was correct. And then one more. And I think I've already solved that one. So just to recap, when we're looking at thinking about solving radical equations, You want to make sure that you get your radical on isolated. You either need to add some values or divide some values to get it to a point like we had here where we'd have to subtract 4, and then we would subtract 4 from both sides. And then when we get it to where there's nothing around the radical, we would then want to square both sides and then begin solving.